Hello and welcome to this virtual session. We're glad you can join us today. Before we get started, there's a few housekeeping items we'd like to go over with you now. Firstly, you can resize the webinar windows to cater to your viewing preferences. You can maximise, minimise and drag the windows to your preferred viewing size. If you look at the bottom middle of your screen, you can click on the widgets that you'll need to get the most out of this virtual experience. Secondly, Microsoft specialists are on hand to answer your questions in real time. So feel free to type in your questions using the Q&A window and we'll answer them as soon as we can. Lastly, we've provided some additional resources for you to supplement your learning. You can access them by clicking on the links in this section. Without further ado, I'll hand over to our speakers.
Welcome to the Microsoft Virtual Training Day for the Data Fundamentals course. So in this training, we're going to take you through the fundamentals of data and database concepts. We're going to take a look at core data concepts, and we'll teach you what relational data is, what that means, what non-relational data is, and what that means, as well as take a look at data analytics solutions in Azure, so that at the end of this training, hopefully, you'll have the skills to both provision and deploy data services in Azure. Now, in Module 1, we're going to take a look at core data concepts. We'll also take a look at some of the roles and responsibilities in data. We'll have a look at some of the relational data concepts as well as non-relational data concepts, and we'll take a look at some of the data analytics concepts in Azure as well. So let's get started with Module 1. So who am I? My name's Michelle, and I am an Azure Technical Trainer at Microsoft, which means my job is to help upskill people to the cloud. Now, previous to this, I was an Azure specialist and an Azure TSP. So I've been doing Azure for quite a while. Outside of Microsoft training, teaching, and working, I like to travel, and I'm a big foodie as well. So I follow where my nose takes me. I also do a bit of coding and writing in my spare time. So if you're interested, you can find some of my blogs on my social media. Now, on the top right corner there, you'll see a big Azure Data Fundamentals badge. Now, if you sit the DP900 exam and you pass it, this is the certification that you'll get. So you'll get the Azure Data Fundamentals certification as well as a badge that you can use to show off. Now let's take a look at the course agenda for this training. We've got 4 modules in this course, starting with Module 1, where we're going to explore core data concepts. And so we're going to have a look at some of the roles and responsibilities in data. We're also going to talk through some of the relational data concepts and non-relational data concepts, as well as concepts to do with data analytics. In Module 2, we're going to explore relational data in Azure a little bit more in depth. So we're going to have a look at some of the relational data offerings in Azure, how to provision and deploy relational data offerings in Azure, and how to query relational data in Azure. In Module 3, we're going to explore non-relational data in Azure. And so again, we're going to have a look at how to provision and deploy non-relational data services in Azure. And we're also going to have a look at how to manage non-relational data services in Azure. And finally, we're going to wrap up with Module 4, where we're going to explore modern data warehouse and data analytics in Azure. And so we're going to have a look at what a modern data warehouse looks like, data ingestion in Azure, some of the data storage and processing capabilities in Azure, and finally, we'll have a look at what Microsoft Power BI does. Lesson 1, explore core data concepts. Now, what is data? Well, by definition, data is a collection of facts, such as numbers, descriptions, and observations used in decision making. So you can classify data as structured, semi-structured, or unstructured. Now, structured data is data that adheres to a schema. So all of the data has the same fields or properties. Structured data can be stored in a database table with rows and columns. Semi-structured data is data that doesn't fit as neatly into tables, rows, and columns. Instead, semi-structured data uses tags and keys that organizes it in some sort of hierarchy. And so a typical example of semi-structured data is data stored in JSON format or JavaScript object notation. Now, unstructured data does not follow any schema or structure, nor does it need to be organized in any particular way. So unstructured data can be anything such as video files, image files, text files, or audio files. When we talk about data, we typically talk about transactional versus analytical data stores. So a transactional data store or a transactional system is often what most people consider to be the primary function of business computing. A transactional system records transactions, and these transactions could be financial transactions such as movement of money between bank accounts in the banking system, or it could be a transaction that is part of a retail system, like tracking the payments of a good and services that a customer has paid for. So you can think of a transaction as a small, discrete unit of work. Now, an analytical system is designed to support business users who need to query data and get that big picture overview of their organization. So analytical systems is really concerned with capturing raw data and using it to generate insights. So an organization can then use these insights to make business decisions. So for example, you might be a manufacturing company who wants to find out the trends in the industry and determine which products to continue to launch or launch next to maximize profitability. And so you can use an analytical system to help support that decision-making process. Now, transactional systems are often quite high volumes. Sometimes they can handle millions of transactions in a single day. And so the data being processed needs to be accessible very, very, very quickly. So the work performed by a transactional system is often referred to as an online transactional processing system or an OLTP system. To support this fast processing, the data in a transactional system is often divided into pieces. So for example, if you're using a relational data system, each table involved in the transaction contains the columns necessary to perform that transactional task. So if we're talking about a bank transfer example, then we might have a table that holds information about the funds in an account that might contain the customer account number and the current balance. Other tables not involved in the transfer operation would hold information like name, address of the customer, and maybe account history. Now, splitting the tables out into separate groups or columns like this is called normalization. So normalization can enable a transaction system to cache the information required to perform the transactions in memory and really speed up that throughput to process the data. While normalization enables fast throughput for transactions, it can actually make querying quite complex. So queries involving normalized tables will frequently need to join the data together across several tables to be able to execute that query. And so this can actually make it quite difficult for business users who might need to examine the data. Now, most analytical data processing systems need to perform quite similar tasks, such as data ingestion, data storage, data transformation, data querying, and data visualization. So this is a pipeline of services to build an analytical system. Now, data ingestion is really about capturing raw data. So this data could be taken from devices that are, for example, measuring environmental information like temperature, pressure, or it could be from point of sales devices that's recording items being purchased by a customer in a supermarket, or it could be recording financial data where we are collecting the movement of money between bank accounts, or it could be weather data that's coming from a weather station. And so some of this data can also come from your OLTP systems or your relational databases from on-premises. So to process and analyze this data, we must first store the data into some repository of some sort. And this repository could be a file store, it could be a document database, or it could be a relational database. And then we have to transform and process this data because the raw data might not be in the format that is suitable for querying. What that means is your data could contain anomalies. So these anomalies should be filtered out. And it might require some transformation of some way, shape, or form. So for example, dates or addresses might need to be converted into a standard format. Also, after the data is ingested into a data repository, you may want to do some cleaning operations to remove any questionable or invalid data, or perform some aggregations such as calculating profits, calculating the margin, or any other key performance metrics or KPIs that are used to evaluate how your organization or your business is doing in terms of growth and performance against the industry or in the market. Now, once we've processed and we've transformed the data and we make it ready to be used, we can then start querying and doing some analytics on our data. So this typically happens after we've ingested and transformed our data. During the data querying process, we might be looking for trends. We might be attempting to find certain root causes or problems or issues that is happening in our organization or business. So there are many database management systems that provide the tools to enable you to perform these ad hoc queries against your data and generate regular reports. Now, the data, once we have the results from our queries, we probably want to visualize it and present it in a visual way. And so this is where the data visualization stage happens, because data is usually represented in tables with rows and columns, and it's not as easy to digest in that numeric format or in those tables and documents. And so visualizing the data can often be quite a useful tool to examine the data. And so you can generate charts like bar charts, line charts, plotting the data onto a geographical map if it's geographical data. And you can really illustrate how data changes over time and pick out the trends in your data. So Microsoft actually offers a visualization tool to enable you to do so. The service is called Microsoft Power BI, and it provides a rich graphical representation of your data. Now, data processing is simply the conversion of raw data to some meaningful information through a process. So depending on how the data is ingested into your system, you could process each data item as it arrives, or you could buffer the raw data items and process it in groups. So processing data as it arrives is called streaming, and buffering and processing the data in groups is called batch processing. So in batch processing, the newly arrived data elements are collected into a group. Now, the whole group is then processed at some future time as a batch. Exactly when each of these groups is processed can be determined in a number of ways. So for example, you can process the data based on a scheduled time interval, say for example, every hour, or you could use some trigger. Say, for example, when a certain number of data items have arrived, then we trigger that process to go and batch process it. Some of the advantages of batch processing is that you can process large volumes of data at a convenient time. And so you can schedule that run at a time when, for example, your computers or systems might otherwise be idle. So you can batch process overnight, or you can batch process during off-peak hours. Some of the disadvantages of batch processing is that there is often a time delay between ingesting the data and getting the results. So all of the batch data jobs, input data, must actually be ready before a batch can be processed. This means the data needs to be carefully checked, because if we identify any problems in the data, it can cause the batch job program to crash. And so the input data must be thoroughly checked before the job can be executed. Even very minor data errors like a typo in the dates can actually cause the batch job to not run. Now, in stream processing, each new piece of data is processed as it arrives. So for example, as we ingest that data, we process it in real time. And so streaming handles data in real time. Unlike batch processing, there's no waiting until the next batch interval to then process that data, because we're actually processing each individual pieces of data item as they come in. And so stream data processing is very, very useful for scenarios where we're dealing with new dynamic data that is being generated on a continuous basis. Lesson 2, exploring roles and responsibilities in the world of data. So there are 3 key roles that deal with data in most organizations, and these are data administrator, data engineer, and data analyst. As a data administrator, their main role is really to manage databases, assign permissions to users, store backup copies of data, and restore data in the case of any failures. As a data engineer, their role in data is to work with the data, to apply data cleaning routines and transformations, build out those data pipelines and processes, identify business rules, and really turn data into useful information and prepare it for data analytics workloads. And as a data analyst, their role is really to explore and analyze the data by creating visualizations and charts which help enable an organization to make better and more informed decisions. So some of the common tools that a database administrator might use includes Azure Data Studio, SQL Server Management Studio, as well as the Azure Portal or the Azure CLI. So a database administrator will need to use these tools to configure the overall availability of their data servers and databases. They're responsible for maintaining consistent performance and optimizing the data servers and databases. So they need to work with the stakeholders to ensure that policies are implemented, that the tools and processes are set up in place, and that backup plans are available to recover any data servers or databases that might fail due to some error because of some natural disaster or human-made error. And so they're also responsible for the security component of the data servers and databases, which means they're the ones who grant access rights to users to determine who gets the right to access databases and who doesn't. Some of the tools that a data engineer might use includes Azure Synapse Studio, SQL Server Management Studio, as well as the Azure Portal and Azure CLI. So as a data engineer, their responsibility includes maintaining and managing data privacy within the cloud, as well as on premises. So they're also responsible for managing and monitoring data stores, the data pipelines, making sure that the data performs as expected by doing a combination of cleaning and transformation on the data to prepare the data for data analytics queries. Some of the common tools that a data analyst might use includes Power BI Desktop, Power BI Servers, and the Power BI Report Builder. So data analysts are typically those who design and maintain scalable business models with data. They might also engage with cleaning and transformational activities to further advance their analytics or build reports and visuals to help business decision makers digest that information and the results in a more visually pleasing way. The main goal of a data analyst is really to turn the raw data into insights based on the business's requirements. And then that insight can then be turned into actionable decisions. Lesson 3, describe concepts of relational data. We'll start with tables. So a table is where data is stored in relational databases. They consist of rows and columns, and all the rows have the same number of columns. Each of the columns is defined by a data type. Now, one of the main benefits of a computer database is that they make it easy to store information so that it's quick and easy to find. For example, an e-commerce system might use a database to record information about the products that this particular e-commerce site or organization might sell, as well as some of the details of their customers and the orders that they've placed. And so we have a customers table here, which stores the customer ID, the customer name, and the customer phone number. Now, a relational database provides a model for storing this data and query capabilities that enables us to retrieve this data very, very quickly. So let's say I wanted to look up customer ID 106 from this table. I can see that it's Alex Peterson. In a relational database, you typically model collections of entities from the real world as tables. So for example, a customer is an entity, therefore we create a customer table. An entity generally describes a thing about information which we want to hold inside a database. In the e-commerce example here, we might also create tables for products and orders because they are also entities in the real world. Now, table contains rows, and each of these rows represents a single instance of an entity. So what that means is each row in this customer table contains data for a single customer, and each row in the products table will define a single product in the products table, and each row in the orders table will represent an order made by that customer. Now, the rows in a table can have more than one columns that define the properties of the entity. So the properties in this case would be customer ID, customer name, and customer phone number. And all the rows in the same table will have the same number of columns. And some of these columns are actually used to maintain relationships between tables, which is where relational databases or relational model gets its name from. Typically, when we're designing a relational data model, we need to normalize the data so that we can reduce storage, we can avoid data duplication, and improve data quality. So, for example, instead of storing a replica of the customer's details in the order table, we would split out that data into two separate tables and reference the customer table from the orders table. So the orders table now contains both a customer ID and it also contains a product ID. Now the customer ID relates to the customer ID in the customer table. And similarly, the product ID will relate to the product ID in the products table. And so we typically design a relational database by creating these relational data model. And each table will have these primary keys, so the customer ID in the customer table, order ID in the order table, product ID in the product table. These are all examples of primary key. And the primary key is then used to associate with a foreign key in another table. And so the customer ID and the product ID in the orders table are foreign keys. And this foreign key references the primary key and is used to establish that relationship between tables. Now, another concept to know in relational data is indexes. So an index helps you search for data in the table. You can think of an index over a table like an index at the end of a book. So the index at the end of a book helps you find certain pages relating to certain topics or subjects, so that when you want to find a reference to a particular topic or a subject, you simply have to look it up in the index at the end of the book and then go to that specified page number. Imagine that you didn't have this index. So to find out about a particular topic or subject, you'd have to read through the entire book to be able to find that information out. And so similarly, when we create an index in the database, we specify a column from the table where this index contains a copy of this data in a sorted order with pointers to the corresponding rows in the table. And so when a user runs a query that specifies this column in, say, for example, the where statement clause, the database management system can then use this index to fetch the data much more quickly instead of having to scan through all the tables in the entire database row by row to find out that information. So you can create many indexes on a table. Say, for example, if we wanted to find all the customers for a specific region, then we can create another index on the customer ID column from the customers table. But indexes are not quite free. So an index would consume additional storage space, and each time you do an insert, update, or delete to a table, the indexes for that table needs to be maintained. And so this additional work can actually slow down your database operations. And therefore, if you're deciding to use indexes, you must strike that balance between having indexes to speed up your queries versus the cost of performing your database operations. Now, typically in a table that is read-only or contains data that is modified infrequently, more indexes will actually help improve the query performance. If a table is queried infrequently, but it's subject to a large number of inserts, updates, and deletes, then creating indexes on that table can actually slow your database systems down. Now, a view is a virtual table based on the result set of a query. So in the simplest case, you can think of a view as a window on specified rows in an underlying table. So you can query the view and you can filter the data in much of the same way as you would with a table. Now, a view can also join tables together. So if you regularly need to, say, for example, find the details of customers and the products that they've ordered, you could create a view to do so. Lesson 4, exploring concepts of non-relational data. Now, in a non-relational system, you typically store the information for entities in collections or containers rather than relational tables. So two entities in the same collection can have a different set of fields rather than the regular set of columns found in a relational table. This lack of fixed schema means that each entity can be self-describing. So often this is achieved by labeling each field with the name of the data that it represents. So for example, a non-relational collection for customer entities might look something like this. Now, a key aspect of non-relational database is that they enable you to store data in a very flexible manner, because non-relational databases don't impose a schema on the data. Instead, they focus on the data itself rather than how to structure it. So this approach means that you can store information in the more natural format that might mirror the same way that your applications might query and consume and use it. So if we take a look at this example here, the fields are prefixed with a name, and some fields might actually have multiple subfields. So for example, if we have a look at telephone, we can have a home telephone, a business telephone, a cell telephone. And these multiple subfields are denoted by enclosing them between square brackets. And so if we wanted to add a new customer to this non-relational data store, it's a matter of inserting an entity with its fields labeled in some meaningful way. Now, the application that queries this data must be prepared to actually pass the information in the entity that it retrieves. The data retrieval capabilities that a non-relational database can actually vary. So each entity should have a unique key value. For example, the ID needs to be unique. So the entities in the collection are usually stored in some key value order. For example, the key here is ID, name, telephone, and address. And the value would be 1, Mark Hansen, the phone numbers and addresses of Mark Hansen. The simplest type of non-relational database enables an application to either specify the unique key or a range of keys as the query criteria. And so in this example, the database would enable an application to query customers by ID only. Now, filtering data on other fields would actually require us to scan through the entire collection of entities, parse each entity in turn, and then apply the query criteria to each entity to find the matches. And so, for example, if we were to do a query that fetches the details of the customer by ID, we can quickly do so. But if we had a query that attempted to find all the customers with the UK address, for example, we would have to iterate through every entity, and for each entity, examine each field in turn. And so you can imagine a database that contains millions of entity records. This kind of query would actually take a considerable amount of time to run. And so you would typically query a non-relational database with its unique key value for each entity. Some of the more advanced non-relational systems support indexing, much like the indexing in the relational database. So queries can then use the index to identify and fetch the data based on a non-key field. Some of these more advanced non-relational systems that supports this are, for example, Azure Cosmos DB, which is a non-relational database management system that's available in Azure. And so with this indexing, we can actually query non-key fields from a non-relational database. Now, semi-structured data is data that contains fields, and the fields don't have to be the same in every entity, so you only define the fields that you need on a per entity basis. The data must be formatted in such a way that an application can then parse and process it. And one of the more common ways of doing so to store the data for each entity and fetch it is using JSON. So JSON stands for JavaScript Object Notation. It's a format that's typically used by JavaScript applications to store data in memory, but it can also be used to read and write documents to and from files. So typically, a JSON document is enclosed in curly braces. Each field has a name followed by a colon and then the value of the field. The fields can contain simple values or could contain sub-documents, each also starting with its own curly braces. Fields that contain multiple values are held in arrays, and the arrays are the values that's denoted in square brackets. Inside these values, you can actually define whatever you like. So the important point to make here is that as long as you follow the JSON grammar, you can import any type of data into the value. Now, when an application reads a document, it needs to use a JSON parser because this JSON parser will then break up the document into its component fields and extract out the individual pieces of data. Now, a row is a row-based format. So it was actually created by Apache. Each record contains a header that describes the structure of the data in the record. The header is actually stored as JSON, and the data is stored as binary information. So an application will typically use a header to parse the binary data and extract out the fields that it contains. Azure is actually quite a good format for compressing data and minimizing storage and network bandwidth requirements. Now, ORC or RC stands for Optimized Row Columnar Format, and it organizes data into columns rather than rows. So it was developed by Hortonworks for optimizing read and write operations in Apache Hive. Apache Hive is a data warehouse system that supports fast data summarization and querying over a very large data set. So Hive also supports SQL-like queries over unstructured data. Now, an ORC file contains strips of data. each strip holds the data for a column or set of columns. A strip contains an index into the rows in the strip, and so the data for each row, and there's also a footer that contains statistical information. So this statistical information are things like the sum, the count, the max and min of that particular strip of data, which you can access. And Parkey is actually another columnar data format. It was created by Cloudera and Twitter. Parkey file, they contain row groups. So data for each column is stored together in the same row group, and each row group contains one or more chunks of data. So a Parkey file includes metadata that describes the set of rows found in each chunk. Now, an application that can then use this metadata to quickly locate the correct chunk for a given set of rows and retrieve the data in the specified columns for these rows. So Parkey is it's developed for storing and processing nested data types quite efficiently, and it supports very efficient compression and encoding schemes as well. Now, unstructured data is data that doesn't naturally contain fields. So examples include video files, audio files, and other types of media streams. Each data item is a blob or binary data, and so you can't actually search on any specific elements inside this kind of data. You might, for example, use Azure Blob Storage to store this unstructured data. So blob actually stands for binary large object. And in Azure Blob Storage, block blobs are supported. So block blobs is used for basic read and write operations, and it has no internal search capabilities. So you could also consider, for example, files as a form of unstructured data. Although some files actually have metadata that kind of describes what the contents of this file might contain. So you can think of an image or photograph as a file, Word document as a file, Excel spreadsheet, they're all files. And some of that metadata for the files might include who the owner of the file is, when that file was created. So all the properties of the file, that's all the metadata. But the main content of the file itself is actually unstructured. Now, you might have heard or seen the term NoSQL floating around when you're reading about non-relational databases. NoSQL is rather a loose or generic term that refers to or simply means non-relational. So some people debate that NoSQL means not SQL or not only SQL, but essentially it just means non-relational data. Now, NoSQL or non-relational databases generally fall into 4 categories. So we have key value stores, document databases, column family databases, and graph databases. Now, a key value store is the simplest and often quickest type of NoSQL database for inserting and querying data. So each data item in the key value store has 2 elements. It's got a key and a value. And the key uniquely identifies the item, and the value holds the data for that item. So this value is opaque to the database management system, which means the database management system only sees the value as an unstructured block of data. Vice versa, if the value was not opaque, so transparent, that means the database management system actually understands all the fields and how that particular data is organized. So a relational table, for example, has a transparent structure. Now, to query a key value store, we must specify the keys which identifies the items to be retrieved. So you can't search on the values. So an application that retrieves data from a key value store is responsible for parsing the contents of the values returned. And write operations for a key value store is typically restricted to inserts and deletes only. So if you need to update an item, you must first retrieve the item, modify it in memory, and then write it back to the database. So it's typically a retrieve, modify, and insert right back to the key value store. The focus of a key value store is really the ability to read and write data very, very quickly. And so that's why search capabilities are secondary. So key value stores are great for data ingestions where we're dealing with a large volume of data that's coming in continuously as a stream and needs to be stored very, very, very quickly. Azure Table Storage is an example of key value store, and the Azure Cosmos DB actually implements a key value store using the table API. Now, in a document database, the data is stored as documents, and each document has a unique ID. But the fields in the documents are transparent to the database management system. So document databases typically store data in JSON formats, but they can also use other types of encoding. So it could be XML formats, YAML formats, or binary JSON. Documents could even be stored in plain text. So the fields in the documents, they are exposed to the storage management system, which enables an application to query and filter the data by using the values in the fields. Now, typically, a document contains all the data for an entity. So what items that might constitute to an entity are application specific. For example, an entity could contain the details of a customer, its order, or a combination of both. So a single document might contain information that would typically be spread across several relational tables in a relational database management system. A document store does not require all the documents to have the same structure. So this kind of free-form approach means we have a lot of flexibility in terms of the data that we insert into the document store. And applications can store different data in documents as business requirements change. And so an application can then retrieve the documents by using the document key, and this key is the unique identifier for the document. So some document databases can create this document key automatically. Others might require you to specify which attribute of the document to use for the key. The application can also query documents based on values of one or more fields, because some document databases might support indexing to facilitate this fast lookup of documents based on the fields instead of the key. So most document databases, they are used to ingest large volumes of data very rapidly in comparison to a relational database, but they're not as optimal as a key value store for this kind of processing. The main goal of document database is that it has that search query capabilities that a key value store typically doesn't have. Now, Azure Cosmos DB actually implements a document database using its core SQL API. A column family database organizes data into rows and columns. So examples of the structures includes OC and Parquet files. So a column family database can appear very similar to a relational database, at least conceptually. But the real power of a column family database lies in its denormalized approach to structuring sparse data. So you can think of a column family database as holding tabular data comprising of rows and columns, but you can divide the columns into groups known as column families. So each column family holds a set of columns that are logically related together. Say, for example, we can use a column family database to group data into two column families that might hold both customer information and housing information. And then we can fetch for both customer information and housing information at the same time with a single query. Now, an analogy that I like to use to explain column family databases a little bit more is let's imagine I held a virtual video treasure hunt through YouTube. I uploaded 10 videos to YouTube. Each video are 10 minutes in length. And I tell you that I have hidden a secret letter inside each of these videos. Now, if you were able to find each letter and you can combine it to form a word, then the secret word is actually the location to the prize for the treasure hunt. Now, after watching a couple of these videos, you notice that I've hidden the secret letter at exactly the 4-minute mark for every single video, which means if you go to the 4-minute mark for every single one of these videos, you'll be able to find the secret letter and in turn, the secret word. Now, in this analogy for a column family database, the video is essentially the column, the group of 10 videos is the column family, and each second of the video represents a row in each of the columns. And the 4-minute mark is actually the key used to fetch the data for the rows in each of the columns. So you should always implement your column families to be most optimal for some of your most common queries that your applications might need to perform. Each row in a column family database contains a key, and you can fetch the data for a row by using this key. So in most column family databases, the column families are stored separately, and the data for a single entity that spans multiple column families will have the same row key in each column family. One of the most widely used column family database management system is Apache Cassandra, and Azure Cosmos DB actually supports the column family approach through its Cassandra API. Now, a graph database stores two types of information. So there is nodes and edges. Nodes you can think of as an instance of an entity, and edges specify the relationship between nodes. So both nodes and edges can have properties that are used to describe the relationship between one another. Additionally, edges can also have a direction indicating the nature of the relationship. So the purpose of a graph database is to enable an application to perform queries quite efficiently by traversing the network of nodes and edges to analyze the relationships between the nodes or between the entities. If we take a look at an example, let's imagine that we are representing all the employees in an organization with the graph database or graph model. And so each node represents an employee, and the edges represents the reporting line for each of the employees. And so in this graph, the arrows on the edges show the direction of the reporting line. So with this structure, this kind of graph model and database, we can ask questions like, find all the employees who report to the IT manager, for example, or we can ask questions like, find out who works in the same department as me. So for large graphs with lots of entities and relationships, you can perform these very complex queries quite quickly. And so we can use graph databases to traverse the network of relationships and help provide answers to those type of complex queries. In SQL, how you would normally do these kind of queries is that you might have to do a lot of recursive joins, operations, and nested subqueries, which can actually become very, very expensive and slow to do. So Azure Cosmos DB supports graph databases through the Gremlin API. The Gremlin API is a standard language for creating and querying graphs. Lesson 5, exploring concepts of data analytics. So data analytics is concerned with taking the data that your organization produces and using it to establish a picture of how your organization is performing and what you can do to either improve or maintain that performance. So data analytics helps you to identify both strengths and weaknesses in your organization, and it helps you make the best business decisions based on some of the results. So the data that a company might use can come from many sources. Now, in a data analytics solutions, you would typically combine all this data from your many sources and construct a data warehouse where you can then use it to ask questions about your business operations. Building a data warehouse will require you to capture the data that you need and transform it into an appropriate format for you to do those kind of querying and data analytics workloads. You can then use visualization tools to examine the information presented by your data and help identify trends, issues, problems, causes to your organization. Now, typically, to start the data analytics process, we begin with data ingestion. So data ingestion is the process of obtaining and importing data for immediate use, or we can store it in a database. So during the data ingestion process, data could be ingested through a continuous stream, or it could come in batches. The purpose of the ingestion process is really to capture this data and either process it immediately or store it. So during the ingestion process, we might do some filtering. For example, if we are ingesting data that could come from a suspicious, corrupt, or data source. And so suspicious data might be data that is coming from an unexpected data source. Corrupt or duplicated data could be due to some device malfunctioning, or there might be transmission failures, or someone might be tampering with the data. During this stage, it's also possible to do some transformation to the data. So we can convert some of that data to a more standardized format for processing later. So for example, if we're talking about dates and times, we might want to reformat it so that all the data that's been ingested will use the same date and time representation. Or if we're talking about measurement data, for example, we might want to convert it so that they all conform to the same metrics. But if we're doing transformation at this stage, remember to keep them quick. Don't want to run any complex calculations or aggregations during the data ingestion stage. If you do need to, then store the data first and we'll come and process it later. Which leads me to data processing. So the data processing stage generally occurs after the data has been ingested and or collected. So data processing takes the data in its raw format and it cleans it, converts it into a more meaningful format that can then be stored in tables or graphs or document databases and so on and so forth. So the results can then be used to perform queries and generate visualizations to be consumed by employees throughout the organization. Now, the aim of data processing is really to convert the raw data into a business model. So a business model describes the data in terms of meaningful business entities, and we might want to aggregate some stuff together to summarize information. So the data processing stage, we could also use it to generate predictive and analytical models from the data. Data processing can actually be quite complex. So it might involve automating a lot of scripts. You might have to use tools like Azure Databricks, Azure Functions, Azure Cognitive Services to examine and reformat the data and generate those models. So a data analyst could then use machine learning to help determine future trends based on the models that's been created from the data. Now, the data processing mechanism can take two approaches to retrieving the ingested data and processing this data to transform it into one of these business models and then saving the transform data and models. So these two approaches are known as ETL and ELT. ETL stands for extract, transform, and load. So the raw data is retrieved and transformed before being saved. So during the transform stage, the data might get standardized, clean, transformed, aggregated. Some of the missing values could be filled out, corrupt data could be chucked out. Other tasks could involve some basic data cleaning, deduplicating data, and reformatting some of the contents of the data. So once the data is in a standardized format that is suitable for analytics, it gets loaded into a repository system. The extract, transform, and load steps can be performed as a continuous pipeline of operations. So ETL is quite suitable for very simple and basic models that has very little dependency between items. The alternative approach to ETL is ELT. So ELT is short for extract, load, and transform. So this process is slightly different because the data is first stored before it's transformed. So the data processing engine can take an iterative approach by retrieving and processing the data from storage before writing the transformed data and models back to storage. Now, ELT is more suitable for constructing complex models that depend on multiple items in the database, often using periodic batch processing. ELT is also a more scalable approach that is suitable for cloud workloads because it can make use of the extensive compute power of the cloud. So ELT is more stream orientated than ETL, because with ETL we can filter the data before it's stored, which is good for data privacy and compliance, as we can remove any sensitive data before we store it. However, ELT, we can't do that because we load the data before we transform it and process it. So Azure provides a couple of options for you to implement both ETL and ELT. So for example, if you're storing data, you can store data in an Azure SQL database, and then you can use the SQL Server integration services to build out your ETL and your ELT pipelines. The SQL Server integration services can extract and can transform data from a whole range of sources, such as XML data files, flat files, relational data sources, and then load the data into one or more destinations. Another approach is to use Azure Data Factory. So Azure Data Factory is a cloud-based data ingestion service that allows you to create those data-driven workflows and pipelines for orchestrating data movements and transforming data at scale. So with Azure Data Factory, you can create and schedule data-driven workflows, also called pipelines, that can ingest data from a lot of different data sources. And you can build quite complex ETL processes that transforms data visually with data flows. Or you can use other compute services like Azure HD Insight, Azure Databricks, Azure SQL Database to do some of that transformation as part of the pipeline. Once we process our data, we've gathered insights and results from our analytics and queries, we can visualize the information that our business models we built present using data visualization tools. So to start the visualization piece, we generally start with creating reports to report on some of our findings and results. So reporting is the process of organizing data into informational summaries to monitor how different areas of an organization is performing. So reporting helps companies, for example, monitor how their online business is doing. They can find out what's not performing well. Good reporting should actually raise questions about businesses from its end users. And using reporting, we can find out things that's happened, and then we can use analysis to explain why certain things happened and what we can do about it. Now, business intelligence, or BI, refers to technologies, applications, and practices for collecting, integrating, analyzing, and presenting business information back to the organization. So the main goal or purpose of business intelligence is really to support better decision making. Now, business intelligence systems can provide historical, current, and predictive views of the business operations. And often they can use data that's been gathered in a data warehouse, or they could use data that's from live operational data systems. So some of the things that they might be able to do is present an interactive slice and dice pivot table analysis, visualize that data, or do some statistical data mining with the data. So we could also create application as part of the business intelligence process to tackle particular areas in the organization, like sales or production or financial, to really track how the business is performing against the industry and against the market. So data visualization helps you to focus on the meaning of data rather than looking at the data itself. So a good data visualization enables you to quickly spot trends, anomalies, and potential issues. Some of the common forms of visualizations that you might use include bar and column charts, line charts, matrices, key influences, tree maps, scatter plots, a bubble chart, or a field map. So with bar and column charts, they allow you to see how a variable changes across different categories. With line charts, we can see how the overall shape of the values are doing over a period of time. With matrices, these are generally a tabular structure that summarizes data. And so often report designers use matrices in reports or dashboards to allow the user to select a particular component and see its significance across the data. Key influences are charts that displays, who the major contributors to a particular result or value is. So key influences are great for understanding, what particular factors influence a specific key metric. Tree maps are used as charts of colored rectangles, so that the sizes of the rectangle generally represents the relative value of that item, and so they can be hierarchical. So rectangles can also be nested within other rectangles. Scatter plots or scatter charts can be used to show the relationship between two numeric values, and a bubble chart is essentially a scatter chart that replaces the data points with bubbles, and so the bubble size represents its relative data points in the data. And a field map is, if you've got geographical data, you can actually use a field map to display how a value differs in proportion across a geography or region. And so you can see the relative differences with shadings that range from light, which generally means less frequent, or lower, to dark, which means more frequent or more. Now, just to wrap up on data analytics. So data analytics is really about examining, transforming, and arranging data so that you can study it and extract useful information out of your data. You can often categorize data analytics as descriptive, diagnostic, predictive, prescriptive, and cognitive. So descriptive analytics is all about asking and answering questions like, what is happening in my business? So descriptive analytics helps you answer questions about what has happened based on historical data. It uses techniques to summarize large data sets to describe outcomes to stakeholders. So examples of descriptive analytics includes generating reports to provide a view of an organization's sale and financial data. With diagnostic analytics, this is really used to answer questions like, why is this happening to my business? And so with diagnostic analytics, we generally use it to help find out what the root cause of something is, why something had happened. And it's really about taking the findings from descriptive analytics and diving a little deeper to find out the cause. And so generally in diagnostic analytics, we take 3 steps to this approach. So we identify the anomalies in the data. So these could be unexpected changes in the metric or particular market. Then we collect data that's related to these anomalies. And then we use statistical methods to discover relationships and trends that could explain these anomalies. In predictive analytics, this is all about trying to find out quick answers to questions like, what is likely to happen in the future based on previous trends and patterns. So predictive analytics is really used to help answer questions like what will happen in the future. We can use techniques that uses historical data to identify trends and determine if it's likely to reoccur. And some of these techniques includes things like statistical and machine learning techniques, such as neural networks, decision trees, and regression. And with prescriptive analytics, this is really used to help answer questions about what actions needs to be taken to achieve a particular goal or target. So by using insights from predictive analytics, data-driven decisions can be made. So prescriptive analytics allows business to make informed decisions in the face of uncertainty. So with prescriptive analytics, we can rely on machine learning strategies to find patterns in a large data set. And we can also analyze past decisions and events that's happened and figure out what the likelihood of it being happened again or likelihood of different outcomes that could happen. And finally, cognitive analytics. Now, this type of analytics is inspired by how the human brain works. So how we process information, how we draw conclusions, how we codify instincts and experiences into learning and understanding. So cognitive analytics really attempts to draw inference from existing data and patterns, derive conclusions based on existing knowledge bases, and then add these findings back into the knowledge base for future inferences. So this is a self-learning feedback loop. So cognitive analytics really helps you to learn what might happen if circumstances change and how you might handle these situations differently. And that's it for Module 1. So we just had a look at some core data concepts, relational data, non-relational data, and data analytics concepts as well. So let's take a 10-minute break, and I'll see everyone back here in 10 minutes to start Module 2.